All right, we're going to start chapter 6 of this workshop, the last session. And this chapter is about applications of photoluminescence. And we've probably touched on these from time to time, and those of you that are in my group hear about a lot of these or even work on things directly related to these. So there won't be a ton of new information, but it'll kind of show how a lot of the concepts that we've learned and a lot of the classes of compounds that we discussed last time have technological importance outside of just the sort of fundamental studies that we normally do. I forgot to ask, did you guys notice that this is a photo that Yenny sent me?
Yeah.
They used it for the cover of the book, so thank you for that. It's been up there the whole time. I never mentioned it before. All right, so on to the so if you've read this chapter, or the way it's sort of organized is kind of into different areas that photoluminescence is important in. And so the first of those is just using photoluminescence as a research tool. And this is kind of an extension of things that we've mostly talked about. But what are some ways that in a research setting photoluminescence is used? Now, as we all know, it's very important for studying fundamental chemistry, especially structure property relationships in photoluminescent compounds. It gives us information about the energy and the dynamics and the character of excited states. So all that information that we want to learn about, whether it's a charge transfer state or not, whether the kinetics of different processes that can happen, all of that we get by studying photoluminescence in a rigorous fashion like we've described. And then if you're going to evaluate something for another application, so if you want to apply it technologically or in some other field, obviously studying photoluminescence gives you an idea of whether it has the appropriate characteristics for that, because every application has different requirements and different properties that are necessary for it to succeed before you would even begin evaluating it in that context. So the sort of just studying it in the research setting is helpful for that. Now, the other area where photoluminescence is very commonly used is in kinetics measurements. And I'm not talking about just measuring the radiative and non-radiative rate constants, but actually measuring reaction kinetics, where you monitor something that either has increasing or decreasing fluorescence as it converts from reactant to product. So basically the change in fluorescence intensity gives you a readout. So one aspect of this is Stern-Volmer that we discussed in chapter 4. That gives us information about kinetics of electron or energy transfer processes. But the other area that we haven't seen yet is a lot of people use fluorescence in particular to monitor enzyme kinetics. So they'll do enzymatic reactions on fluorescent molecules, where again the fluorescence is either quenched or increased as the reaction progresses, and then you can use the fluorescence intensity as a readout of concentration. And the reason it's useful for enzyme kinetics in particular is because you can do it at micromolar scales. Usually for enzymes you don't have a lot of material to work with, so you have to run the reactions at low concentration. And fluorescence is well suited to do that. You can't use NMR, for example, to do enzyme kinetics. You just don't have enough material. Now, one thing to be aware of, we're not going to go into all the details of this, but there are references, or at least one reference in the book that kind of touches on this issue, is that we already talked about all the way back in probably chapter 2 or chapter 3 of this, that when you read out the fluorescence intensity, there are a lot of factors that influence it. It's not just always going to be directly proportional to concentrations. It depends on the absorption at the excitation wavelength and things of that sort. So, and also instrument settings and the like. So if you're using fluorescence intensity as a readout for concentration, as you often do in kinetics measurements, you do need to be careful that the observed intensity is not skewed in some way by those other factors. So that's something important to realize. So not everybody that does enzyme kinetics in this way realizes that, and so you'll see some data that's out there that's interpreted incorrectly because of other factors besides concentration that influence the intensity that people observe. All right, so those are some just things that we would use it for in a research setting, but what we want to get into for the rest of this is actually, applications that have, that have importance outside of a chemistry lab. So they might be important in biology and medicine, or technology, something outside of the field of chemistry where photoluminescent molecules are used. Now there's some that I'm not going to talk about that you're probably familiar with from your everyday life, like fluorescent paints, for example. A lot of road signs use luminescent paints because they're easier to see, especially at night, once they're illuminated by headlights, or home decorations or things for your room when you were a kid that are luminescent, stuff like that. But we're going to talk about, again, primarily things that are more in the realm of science and technology in this part. So the first one we'll get into is small molecule luminescence sensing, which we do work on a little bit in our group, so this is something that you guys are a little bit familiar with at least. And so the definition is that we're talking about a situation where you have a measurable change in photoluminescence in response to an analyte, whatever you're trying to detect being the analyte. And so this has applications in chemistry and biology and probably other areas too, environmental things as well, where you're trying to, again, accurately measure some chemical species and you're using luminescence as the readout to do that. Now, the interaction between the sensor, which is a luminescent molecule, and the analyte, which is what it's measuring, that can usually occur in solution. So usually it's, these are liquid phase measurements, but it can also be interfacial. You can have a sensor that either responds to changes at the surface as a molecular sensor that binds to a surface, or you can have the surface be your sensor if it's luminescent, which then changes as different things bind to that surface. So there's a few possibilities, but again, the vast majority of these types of things involve studies done in solution. And there's 3 types of response you can get when you do luminescence sensing. So the first of these is a turn-off response. This is when the photoluminescence is quenched in the presence of an analyte, meaning that the intensity or the quantum yield of your photoluminescent is reduced as the analyte concentration increases. So this is sort of a idealized spectral profile, what it looks like. So in this color scale, blue is when you don't have any analyte present, yellow is when there's higher concentration, and so as you progress to higher concentration in a turn-off sensor, you would see the relative emission intensity decrease. All right, and so that's going to be the response for turn-off sensing. Turn-on is pretty much the exact opposite of that. So when the analyte is not present, you have either no or very weak luminescence, and then as you add the analyte, you see the intensity of the luminescence increase. In this case, blue is your starting point where there's no analyte present, and it progresses to red, which is high analyte concentration. Now, does anybody remember, I think we've talked about this before, it's probably been a while, or do you know from your own reading, which of these 2 is desirable? Is turn off better or is turn on better in general?
Usually turn on.
All right, why is that?
Because when it's like, when there's nothing there, if you turn it on, you'll be able to see it like relatively easily. But if the turn off, it's like, if you decrease it a little bit, it might be hard to tell because like there's a lot of color still.
Yeah. So that
A lot of also because for turn off, like it doesn't necessarily analyze in there. I think it just makes oxygen your entire experience.
Yeah. So if it's phosphorescent with the turn off sensing, you have to be especially careful because oxygen will turn off phosphorescence. But that would be true whether it's a turn on or a turn off sensor. That if you have phosphorescent sensor, the oxygen is going to be a problem. So most sensors that have been developed, especially for biological applications, are fluorescent, but there are exceptions to that. Even things that don't detect oxygen can be phosphorescent. You have to be aware of the role that oxygen plays in that. So the answers that were given about, turn on being more desirable were largely correct. You probably can't pick them up through my tablet microphone if you're watching online. But basically the analogy that I learned back in the day when I was first introduced to this topic is imagine you're in a dark football stadium. And so a turn off sensor would be where if everybody's holding a candle in the stadium and one person turns off their candle, then you won't really notice that if that's how a turn-off sensor would respond. But if it's a turn-on sensor, the stadium is initially dark, and if one person turns on their candle, then you'll notice it. So with turn-on, you're much more sensitive, especially at low levels. It's easier to detect what's happening. So when you have a choice, turn-on is desirable, but the third type, which is in some ways even more desirable than either of these 2, is ratiometric. And this is kind of has 2 flavors. So the one that's shown here is the one that's at least more relevant to the type of stuff that we do, where you have 2 separate luminescent signals, and one of them is more or less constant in the presence of analyte, and one of them has a much steeper dependence on the analyte. And so then what you do is your readout is not the absolute intensity of either signal, it's the ratio between the 2. And then this constant one here serves essentially as an internal standard. Now the other way that you can have ratiometric sensing is if you have a signal that they both forms could be luminescent, but if the signal shifts substantially, so you can actually resolve the bound and the unbound forms, then the ratio between those can also be used as your readout. So it doesn't have to be that necessarily one of them is completely unresponsive, but if they're both visible in the presence of analyte and you can read out intensities of both of them at any concentration, that's sort of another slight alternative on how that would work. So you could see it as two signals, one decreasing, one increasing, but if you can resolve the two signals, you can still read it as a ratio. And that's often more reproducible because measuring absolute intensity, as we've now talked about many times in this workshop, is problematic. And so there's a lot of calibration issues that come into play when you're trying to use absolute intensity as a readout, whether it be turn off or turn on. For ratiometric, a lot of those factors get buried because you're able to use that constant signal as your internal standard. All right, so that's how, in a general sense, how sensing works. And then within this, there are many different types of analytes you would want to and are able to sense, and there's still a lot of active research going on how to more effectively do this for certain situations. So one that has been very common sort of came about in the sort of explosion of bioinorganic chemistry research that happened in the early 20th century, early 21st century, especially back around the time that I was in graduate school or even before that. A lot of people started studying metal ion sensing because the increasing recognition of metal ions being important in biology led to a desire to be able to detect those accurately and at low concentrations. So the most common mechanism for metal ion sensing is using what's called the PET mechanism, photo-induced electron transfer mechanism. And so the way this works is that when the analyte is absent, so these are usually turn-on sensors, and so when you don't have metal ions present, the luminescence is quenched by photo-induced electron transfer. So usually you're going to have some sort of electron-rich group with a lone pair, often an amino group on the molecule, that will, in the excited state, donate electron to the luminescent core and quench luminescence. So it's, again, we talked about electron transfer quenching also earlier in this course, and this is basically an intramolecular electron transfer quenching that happens when you don't have metal ion present. Now, when the metal ion is present, the lone pair that's part of that quenching group will bind to the metal ion, and that will basically reduce or eliminate that quenching process because the lone pair now being coordinated in metal is not able to donate to the excited state of the molecule and quench luminescence, so you get a turn-on response. Now, the same sort of thing can happen with H+, so basically anything that lone pair can coordinate to. So you'll get a turn-on response as a result, and the big challenge in metal ion sensing is selectivity. How do you design a sensor that only responds to one specific type of metal ion and not others? Because again, this mechanism can be non-specific because all it requires is that your lone pair be coordinated to something, or protonated is another way that can happen, and you'll get a similar turn-on response. So that requires the design of receptors that are very specifically crafted for a specific metal ion, and a lot of work goes into that to optimize that. But that's from a luminescence standpoint how it works. So this video here is going to show that with sort of a representative example shown in the insight. So this is a very famous zinc sensor that was developed by the Lippard group at MIT. It has a fluorescein core. So we talked about fluorescein as a sort of a common sort of xanthine-based fluorescent molecule in the laser dye category that we discussed. And then these are the zinc binding units. And I think this one can bind up to 2 equivalents of zinc. So there might be a sort of a 2-stage response. But these dipyridyl amines, these methylene-spaced dipyridyl amines, bind to the zinc, and the lone pair that's on this nitrogen is no longer able to donate to the fluorescein and quench luminescence when zinc is present. So the video that should play will show how this works. Maybe. Okay. Yeah, so this type of sensing works for cation. You can have anion-specific ones too, but those are designed differently. So in the absence of metal, that electron transfer quenches luminescence, but then the metal is bound in that pocket. That prevents that quenching, and the luminescence occurs. That's kind of a cartoon of how that works. So that's the typical way for metal ion. There are other modes of sensing. This is far from comprehensive. The nice advantage of doing it this way, if you can get selectivity, is that it's fully reversible. So if you can, in addition, you have to sort of appropriately set the binding constant for the concentration range that you want to detect. And if you're able to do that, then when there's less metal ion present, the metal ion will dissociate and you'll quench luminescence again. So in principle, this can be used for sort of real-time measurements that have a temporal response as well. But again, that requires the appropriate binding constant and that the metal ion be able to rapidly associate and dissociate from that core. So there's a lot that goes into designing these sensors, but the main thing for us to understand is how the luminescence response works, which is by shutting off electron transfer from this lone pair to the fluorophore. That's the most common way that metal ion or pH sensors will work. Now, the type that our group is most familiar with is oxygen sensing. So we'll go through it, but for most of you guys, this introduction should be a review as long as Greg has done his job of appropriately describing it to you. Oxygen sensing is usually turn off or ratiometric. There's probably exceptions that are turn on, but I can't think of any off the top of my head. And there's not an obvious way that you would do that, at least especially in a reversible sense. I think turn on oxygen sensing is possible, but that usually requires a chemical modification of the fluorophore that then irreversibly would detect O2, but it's hard to do it reversibly with turn on. So most of the reversible O2 sensors are turn off or ratiometric. Now the truth of the matter is, almost any phosphorescent compound, especially if it emits from the typical, T1 to S0 transition. If you're talking about phosphorescence from, quartet states and things, I think they might behave a little bit differently in some cases, although they still tend to be oxygen sensitive. But the most common phosphorescent molecules that emit from a triplet state to a singlet ground state, pretty much any of those can serve as an oxygen sensor, because as we talked about already before, these triplet states are quenched by triplet O2. It's a triple annihilation process. So we sometimes get reviews on our paper where they're like, oh, you should really use these compounds for an application like oxygen sensing. And as soon as I read that, then I know that the reviewer either has half a brain or wasn't using their full brain when they wrote that statement, because every phosphorescent molecule can serve as an oxygen sensor. So there's nothing surprising about that, no matter what the compound is. But that's true, but then there's, of course, design elements that go into it. And most fluorescent molecules, in contrast, have very little response to oxygen. Now, it's not quite correct to say that fluorescent molecules don't respond at all to O2. In some cases, they do. It's not usually by an energy transfer mechanism, because energy transfer from a singlet to a triplet is not usually very efficient at all. But some fluorescent molecules are pretty good reductants in their excited state, and so they can still transfer an electron to O2, and that can give a quenching response as well. That's, again, usually not very efficient, because the fluorescent molecules tend to have nanosecond lifetimes, and in the presence of only usually millimolar at the most for O2, you're not going to get a lot of quenching. But you might see a small response for fluorescent molecules, but it's, again, usually insignificant and still to the case that you wouldn't really want to use that as a sensor. But then what ratiometric sensors do is they will usually, in the case of oxygen sensing, they will combine fluorescent and phosphorescent components. So the fluorescent component, as we know, will not respond very much or at all to O2, and that would be your internal standard, and then the phosphorescent component is going to be significantly quenched. And a key sort of design principle in oxygen sensing is the Stern-Volmer relationship, because this quenching response will typically follow that relationship that we introduced a couple of chapters ago. And the Stern-Volmer constant, which is basically the slope of the line that relates the intensity decrease to the concentration of the quencher, is a product of two things: Kq, which is the quenching rate constant, and tau 0, which is the phosphorescence lifetime of the molecule that's quenching. And so in oxygen sensing with triple state molecules, it's usually very efficient, such that Kq is close to or at the diffusion limit. So that basically means at the limit at which oxygen and the molecule diffuse together, you will see quenching. It happens instantaneously as soon as the two come together. And so Kq is usually a pretty similar value for all of these sensors, and that means then the Stern-Volmer constant, the way that you modify that would be by changing the lifetime tau 0. So the phosphorescence lifetime that you have, which we've talked about how to measure it, we've talked about what the significance is already, that's going to be critically important for determining the range of O2 that you can detect and how sensitive your molecule is to O2, again, given by this Stern-Volmer constant. So in general, if you have a long lifetime, you're going to be sensitive to very low levels of O2. If you have a short lifetime, it won't be as sensitive to low levels, but it'll be able to detect a wider range. So being able to synthetically tune the phosphorescence lifetime is critical for changing the profile of an oxygen sensor that operates via the typical mechanism, whether it's phosphorescent or ratiometric. So then here's a diagram of how it happens. So this is just the typical turn-off sensing. And again, these processes we're already a little bit familiar with. This is just diagrammed in a slightly different way. So in the absence of oxygen, you get phosphorescence. And then in the presence of oxygen, the triplet state at a rate competitive with its luminescence is quenched by triplet O2. So in the process, you generate singlet O2 via triplet annihilation, and that reduces your phosphorescence intensity. Ratiometric sensing is sort of similar, except that in this case you have two components, a fluorophore and a phosphor, that are simultaneously excited, and the fluorescence is unaffected. So whether you have oxygen present or not, you get the same color, the same intensity for your fluorescence, but the phosphorescence is quenched by the same mechanism, which then modulates the ratio between the two signals. I didn't want to be too egocentric, so I didn't show our own, but this is a classic example of a ratiometric sensor that has a phosphorescent iridium compound, a fluorescent coumarin, and a bunch of spinach in between to control energy transfer and also to affect bioavailability or biodistribution and things like that. So that's again how they typically work. And there's advantages, especially in the context of intracellular imaging, to have the two things co-localized. You might ask, well, why can't we just mix a fluorescent and a phosphorescent compound together? In principle, you can for some applications, but inside of a cell, there's no guarantee that the fluorescent and phosphorescent component are going to distribute in exactly the same way. So having them attached to each other ensures that that occurs. In other sensing applications, it may be possible to just have a physical mixture of a fluorescent and phosphorescent component, as long as it's a case where you don't need to worry about whether the two are localized together or not, and there's no sort of dynamic component that you're concerned with. All right, so that's how oxygen sensing works. And then the last type of sensing that we'll discuss is fret sensing. So if you have any friends in the Zastro group, they probably are familiar with this, and that they work on it there, and it's very commonly used in the context of biochemistry and biology. So what happens in fret is, we talked about fret also, that's forced or resonance energy transfer, same definition as we gave before, and it has a distance dependence. So when you have two fluorophores that are in close contact, they're able to undergo that energy transfer process. So fret sensing involves two fluorophores usually linked together in some way, or that can be linked together under some chemical stimulus. And it only occurs when those donor and acceptor fluorophore are in close contact. And how close they are depends on some factors besides just the distance. But in general, it means 1 to 10 nanometers apart. So if they get further apart than 10 nanometers, the fret will be negligible, and anything close to that, you can observe it. And fret sensing is very distance dependent. So it has a 1/R6, the dependence that we introduced when we talked about fret a few weeks ago. So basically what happens in fret sensing is that when the donor and the acceptor are far apart, only the donor fluorescence is observed. So you'll just see fluorescence from the one component. You have to selectively excite that one. But then when they come together, you still selectively excite the donor, but there's energy transfer from the donor to the acceptor, and you now start to see fluorescence also from the acceptor. So in some way, this has, when we see the spectral profile, you'll kind of see that it has almost a built-in ratiometric response. Now, this can be used in a lot of contexts. So the question is, how do we bring the two together and force this fret response to occur? I mean, one way is by metal ion binding. So if you have, a donor and an acceptor that cooperatively bind a metal ion, that can be a way to bring them together. So it can be used for metal ion sensing to some sense, but it's also very common in biological contexts to study protein-protein interactions or conformational changes, where basically if two different proteins come together, one that has the donor, one that has the acceptor, you'll see that fret response when the two are close to each other. Or if there's a protein conformational change where the donor's over here, the acceptor's over here, and it folds up and the two come closer together, you'll see that fret response. Now, one thing I'm not very clear on myself, because I don't do fret, is I don't think it's usually possible to be very precise with the distance. It's more or less a binary thing. It's either off or on. So either they're far apart and it's off, or they're close together and it's on. You can't really tell how close they are or how, you might be able to get some qualitative information, but usually it's sort of a binary sort of response that you're looking for. But it's used a lot in biology for that reason, because it does respond to things like protein-protein interactions and conformational changes. And there are some small molecule sensors that use FRET, but it's not particularly common, I would say. So here's the typical FRET response. And as I said, you would typically choose an excitation wavelength where you can selectively excite the donor, because the acceptor fluorescence is not inherently quenched. If you excited the acceptor, it would give rise to fluorescence at its characteristic wavelength. But if you selectively excite the donor, you'll only see the fluorescence from there when the two are far apart. And then when they come close together, again, conformational change or some cooperative binding event that brings them close together, you'll have efficient energy transfer via the Forster mechanism from the donor to the acceptor, and now you'll start to see the acceptor fluorescence dominate. And sometimes you'll have, residual donor fluorescence. You can, again, sometimes read it out in some sense as a ratio of the two, but you'll see that difference in response because you're able to now start generating the acceptor excited state and observing fluorescence from that. All right, so that's how FRET sensing works. Again, something that we have not done, but it is fun to think about maybe how we could do it for some of our stuff, but we haven't really gone down that road yet in our own work. All right, now the next sort of major section is going to be applications of luminescent molecules in biology. So we're going to talk about a few different areas in biology where photoluminescent molecules make their mark. And the first one we'll talk about is on cell imaging. Again, people in the Chen group, Tyan's group, would be involved with this to some extent. And so there's many compounds, mostly organic chromophores, because of their stability, their lack of oxygen sensitivity, their biocompatibility, all that stuff. There's many organic chromophores that are used in microscopy when you're trying to image cells or tissues. Now, a lot of those are just stains. They're just really darkly colored molecules that absorb different colors of light. So like, things like methylene blue. I don't remember all the ones that I used to use in biology. That's one that sticks in my mind because it has a nice blue color. But anyway, these are just basically dyes and they can be designed to go to different parts of the cell, and they have different colors. So when you're imaging them with a microscope, you get this nice coloration, this contrast that you can use to help see different parts of the cell. And a lot of those are, again, just absorbing. They don't really emit any light. But there are also, that should be luminescent molecules, fluorescent molecules in particular, that can be used in another type of microscopy, which is called fluorescence microscopy. So fluorescence microscopy, as the name implies, in addition to just having a bunch of mirrors and cameras and things that detect absorbed light, they also have detectors that can visualize the emitted light, so you can actually see things that are luminescent. And that can sometimes give you even better contrast than you're able to get with just standard microscopy. So most of these luminescent molecules that are used, as I said, they're small molecule organic fluorophores because of their compatibility and all that. And in many cases, they're from the laser dye category. So we talked about that a little bit, I think, last time. This was when we talked about different categories of luminescent molecules. And so those, coumarin, xanthine-based, rhodamines, all those different laser dyes that we learn about, a lot of those are used in fluorescent microscopy, often decorated with functional groups that ensure that they can get into the cell or get to the part of the cell that they need to get into. So those different functional groups and the overall charge of the molecule are important for determining where in the cell it will localize. And so a lot of these have been designed then to be specific, organelle specific or subcell specific stains. And then what you can often do is you can use multiple colors. So, one color for, let's say, the nucleus, one color for the endoplasmic reticulum, trying to dig deep for all my bio terms that I used to know. And you can use multiple colors to image all these different components, and that can give you sort of a more accurate and detailed picture of those subcellular structures than you're able to get with just a standard, dark field microscope or with a standard, using stains and things like that. So here's just some representative examples of cell imaging stains that are fluorescent, used for fluorescent microscopy. There's many of them on the market. As you'll see here, most of them are marketed with trade names. I think DAPI might actually be a chemically relevant abbreviation. diamino phenylindole or something, but or sorry, those are guanidines. But this actually I think is kind of irrelevant. But most of these are named after people or companies or things like that. And a lot of times, actually, what's interesting, well, not interesting, but frustrating, I should say, is it's hard to find the structures of a lot of these dyes. So here's ones that are, I guess, off patent now, and you can find their chemical structures. But a lot of them, they'll be sold by a company with some name, and they'll tell you like what the fluorescent wavelength is. They'll tell you what part of the cell it will go to, but you can't actually find what the chemical structure is because they're still under patent. They're all under, IP control. But these ones are available. So Host dyes, I don't know if I've said that right. And then Alexaflor is a common. There's tons of Alexaflors, and only some of them can even find the structures for. So as the sort of data on this slide tells you, they can go to different parts of the cell. So these top two are both DNA stains. They selectively bind to DNA, and thus are used to sort of image where the nucleus of the cell is. And they can have different wavelengths. These two are actually very similar to each other, but then like the Alexaflors down here, they can actually be specific for different cell components. So they'll sell like different tags and different labels and things that you can easily conjugate to here. So you'll usually buy the stain, and you'll buy some coupling reagent that goes along with it, and by changing that R group, you can change what part of the cell it goes to. And there's different colors, as you can see. So this Alexaflor, again, I don't know where these numbers come from. It might be the wavelength, but it's not quite right. So I don't know if those might just be catalog numbers more than anything. But Alexaflor 488 is sort of in the green region for first fluorescence, and then Alexaflor 647 is in the red region. So there's different colors. And again, in this case, the specificity is determined by whatever you conjugate to it at those positions. These will usually be sold as either like acid chloride or other types of labile functional groups there, and then you can conjugate them to some biomolecule that will then dictate what part of the cell it goes to. So those are very common in cell biology if you ever go into that field in your future life, which I would not recommend, but I won't stop you. I won't stop you if you choose to. All right, and then one other application in biology that we want to mention is photodynamic therapy. Now this one actually does not require luminescence, although most of the compounds that they use for this are in fact luminescent. And so in general, the general term for photodynamic therapy is just, the general definition is any drug that is activated upon light excitation. So the idea is that it doesn't require luminescence, but it often involves energy transfer or photodissociation processes that are somewhat linked to luminescence, or that involve the same excited states that luminescence would come from. So there is some thematic overlap there. The most common photodynamic therapy approaches are oxygen dependent. So they require oxygen present for reasons that I'll get into in a little bit. And it, again, stated here is because what these oxygen dependent photodynamic therapy agents do is there's triple energy transfer to oxygen that generates singlet O2. And then, this singlet O2 ends up being highly toxic to cancer cells. It can induce apoptosis, cell death in other ways. So, the advantage is that it's, highly localized. So basically, you might not have uptake specificity in all cases. One of the biggest challenges in the design of any type of drug is to make sure, especially for cancer drugs, which is what the vast majority of the money goes into now. For those types of drugs, you need to make sure that it only goes to the tumor cells and not to the healthy cells. And sometimes that's not very easy or very possible to do. But the nice thing about photodynamic therapy is that, even if that doesn't happen, even if the drug distributes over your whole body, it's only going to be active in the places that you actually irradiate with light. So it's best used for tumors that are at the surface or that have, a sort of well-defined tumor mass. It's not really useful for blood cancers or things that are really deep in the body, although they can put, they have like methods now where they can put fiber optics like into the body and actually irradiate inside, even if it's not at the surface. So they're advancing the ability to use these for different contexts, but with any cancer drug, it takes a long time to get, approval. And I think at the moment in the U.S. there's only one FDA-approved photodynamic therapy drug. So there's been a lot of effort into it. There's a lot that have gone to clinical trials and even gone pretty far. I think there's only one that's actually FDA-approved fully. It's called Photofrin. It's a porphyrin-based drug. Now, the key criterion that you want to sort of optimize for photodynamic therapy is what's called the phototherapeutic index. So what this is, if you're not familiar with biology, EC50 is basically the concentration at which that compound will cause 50% of cells to die. And so you basically measure that in the dark and in the light. And so an ideal photodynamic therapy drug will have a really low EC50 value in the dark, meaning that it's not toxic at all in the dark. And then when you turn the light on it, the EC value will increase, and it'll be more toxic when it's illuminated. So you want this ratio to be as high as possible. So I think I said the opposite way. So the toxicity should be low in the dark, which means the EC50 is high.
Yeah.
And the toxicity should be high when the light is on, which means the EC50 should be low. Because it's the concentration at which 50% of the cells dies. The more toxic compounds have lower EC50 values. So that's what you typically want to optimize when you're designing a photodynamic therapy drug. If you guys remember Sherry McFarland's seminar from a few months ago, that's what she talked about in hers a lot. For these types of drugs, especially if they're going to be used in humans, you typically want red or near infrared excitation, because that's the light that's going to penetrate the skin and the cells the best. And so those are some of the key criteria for photodynamic therapy. Now, again, the most common one and the only one that I'll discuss in detail involves single oxygen generation, but there are others that involve, photodissociation of ligands, which then can result in biomolecules binding to that and causing toxicity. So there's other ways of doing it. And there's actually a need to find some that are not dependent on oxygen, because a lot of tumor cells are very hypoxic, and so it's actually sometimes hard to do photodynamic therapy inside of a tumor when there's not very much oxygen available for that. So here's how it works, and again, it looks very similar to oxygen sensing, and in fact there is a lot of overlap. So, a near miss in one area might be a direct hit in another. So something that doesn't work very well as an oxygen sensor could actually be a good photodynamic therapy drug, or vice versa. Again, for photodynamic therapy, you don't need it to be very luminescent. You just need it to be having excited state that's efficiently quenched. So you'll get the, excitation, intersystem crossing to the triplet state, energy transfer with O2, and then singlet oxygen causes cell death in different ways. It's pretty complicated, but it's not very good for cells. It does a lot of reactions with key biomolecules, because singlet O2 is very kinetically reactive, much more kinetically reactive than triplet O2. And that triggers cell death. This actually reminds me of something that's important to realize in just general everyday human life. We would not exist if oxygen did not have a triplet ground state. Because oxygen is very oxidizing, as the name implies. That's where the word oxidizing came from, but it's kinetically a very poor oxidant because it is a triplet state. So if oxygen existed as single oxygen, we wouldn't be here today. So, but by intentionally producing single oxygen, then we can kill things that we want to kill. So and that's been developed. But as I said, as much effort has gone into it, as far as I know, there's only one that's actually FDA approved completely. So it's been a challenge, but it has a lot of promise nonetheless. All right, the last major category of applications we'll talk about are applications in technology, which physics, engineering, all involved in developing these technologies, along with the chemistry of the luminescent components. And the big one here is electroluminescence, which, as the name implies, involves using electricity to generate luminescent excited states. So the difference here is, instead of photoexcitation, which promotes an electron from a HOMO to a LUMO, you're using electricity to generate electron hole pairs, where if you want to think about it in terms of HOMO and LUMO, I don't have a diagram of this, but essentially you're simultaneously removing an electron from the HOMO and adding an electron to the LUMO. So you have a bias setup that allows you to do that, and so that effectively generates the same type of excited state, and then those can recombine to produce light. Or very often in devices, though, that energy is transferred to another luminescent molecule that then produces the light. So it can happen in different ways. But it's electricity being used as the excitation source rather than light. So the most successful, arguably the most successful category of electroluminescent devices are LEDs, and solid state LEDs are the ones that have become almost common, and in many cases, depending on environmental regulations, more or less mandatory in home and office lighting applications. These ones are probably fluorescent still, but you know, a lot of, basically all the regular sort of light bulb shaped things are more or less by default LEDs now. It's hard to find non-LED light bulbs anymore. And so these are all solid state LEDs. Then, you know, they're based on solid state materials, as the name suggests. And the way that they work is they usually have a blue emitting semiconductor. So it'll be something like gallium nitride, which is electroluminescent in the blue region. But then to produce the rest of the spectrum, they would coat that with a solid state phosphor that has broad emission over a larger part of the visible spectrum. So the phosphor that's coated on the blue emitting component will absorb some of that blue light energy and then re-emit it as lower energy light. So really a typical LED combines electroluminescence and photoluminescence. So electroluminescence generates the blue light, and then photoluminescence excites the other phosphor that's coating it and generates the rest of the light. So it's kind of those two things combined. So here's kind of what it would look like for a typical LED profile. This one is simulated, but it looks not too different than what you'll find in LEDs, where you have your semiconductor, your gallium nitride, or some other semiconductor that generates a relatively sharp blue band, and that's going to be interfaced with usually a rare earth phosphor, so something that has you know, a lanthanide element as the key component. We talked about those last time. Typically those emit by those F to D transitions. It's not an FF transition, but an F to D transition, which gives this broad appearance. And by the combination of the blue light with the broad band from the phosphor, you can get more or less white light. And obviously tuning the ratio of the blue and the other components is important, and how broad the profile is. All those things dictate the color, you know, the warmth of the color, whether there's a you know, cold white or a warm white. All those different descriptors you see on LED packaging are determined by the color profile of the two components and the ratio of those two components that are present. So that has to be optimized to make it, you know, comfortable for the human eyes and able to, you know, light up all the colors that we see appropriately and all that stuff. So that's how solid state LEDs work. So if you're friends with anybody in the Burgage group, that's a topic that they're still very much interested in. And then the other type of electroluminescent device that's more relevant to our work that we all know about is organic light emitting diodes, OLEDs. And you know, there are people that are working on these for, you know, home and office lighting, but I don't think they're going to make really a big mark in that field, because usually the most efficient OLEDs use precious metals, which you can't really, you know, have enough of, or they're just way too expensive to use for large scale things. But they're exceptionally useful for color displays, because they do have pretty good power efficiency. So especially for handheld devices, you don't have to worry about battery consumption too much, and they just give exceptionally sharp colors. And the other nice thing about an OLED is, because they're electroluminescent, you don't need a backlight for an OLED. So a lot of, you know, TVs that are not OLEDs, they have a backlighting panel that excites the pixels that actually give the colors that you see. And so because of that, when you have, you know, black on the screen, is not truly black, because a little bit of that backlighting bleeds through. But for OLEDs, you can completely turn them off, and so your black is like truly black in an OLED. It gives you better contrast, especially for those, you know, if you like Star Wars movies and things like that, where you're going to have all that dark background all the time. So OLEDs are layered devices, usually a few hundred nanometers thick, and they're of varying complexity. So really, at minimum, you just need 3 layers: an anode, a cathode, and an emissive layer. But in most cases, they're much more complicated than that. Now, however many layers you have, whatever luminescent molecule you're using to generate your light is doped into the emissive layer, which is going to be abbreviated as EML. And so molecules that use triplet excitons are the most efficient. And we'll get into that a little bit more in a second here, but that means either phosphorescent molecules, which is what we work on, or thermally activated delayed fluorescence, TADF, that we also talked about. Both of those can effectively use triplet excitons, and they would have much higher efficiencies than you can get with just simple fluorescent molecules. So here's a typical device architecture. This one has 5 layers in between the cathode and anode, but they can have fewer layers than this, more layers than this. I mean, really, I'm not sure what the commercial devices use. They're probably at least this complicated. But anyway, what you have is an anode and a cathode. That's how you provide the electrical bias that powers the device. And again, the emissive layer is sort of the business end where the light is generated. But in addition to that, you have an electron transport layer, often a hole blocking layer, hole transport layer, hole injection layer. That all those are really doing is making sure that the excitons are efficiently collected at your emissive layer. Because if you generate an exciton, but the electron and the hole recombine before they diffuse to the emissive layer, that's basically wasted energy. So these complex layering structures that you often have in OLEDs, they're usually designed to make sure that you can maximize efficiency by getting as many of your excitons as possible into the emissive layer before they recombine. So you basically want to prevent recombination and get efficient transfer to that center layer. And that's where your emissive dopant is going to be. Now, for a typical OLED device that uses phosphorescent or TADF emitters, the emissive part is actually doped in at a relatively low level, about maybe 10% or so in general weight percent in the emissive layer. So most of the OLED components, most of the weight of the OLED is actually the other components. The emissive part is just a small fraction, which is another reason why there's not really much concern with using iridium for OLEDs, because you use a very tiny amount of it compared to the cost of all the other materials that go in. So there's not really a huge incentive there. Now, the efficiency of an OLED is shown here. So this external quantum efficiency, as it's usually quantified as, abbreviated as eta. So that is essentially going to be a ratio of the number of photons emitted from the device divided by the number of charges put into the device. As you measure using the current that you're putting in. And that's going to be a product of 4 factors here. So eta R is the ratio of injected charges that produce excitons. So again, we talked about the importance of having often multiple layers to ensure that this value is as high as possible, that every time you inject a charge into the anode and the cathode, those recombine only in the emissive layer to form an exciton. They're not recombining before that and wasting electricity. Chi here is the ratio of those excitons that are used by the dopant, and this is where the luminescence mechanism of the dopant is critically important, because of spin statistics, the excitons that are generated are going to be 25% singlet and 75% triplet. There's really nothing you can do about that to change that ratio. That's just quantum mechanics, which are usually difficult to fight. So if you use a fluorescent dopant, they can only use the singlet excitons, which means that chi and thus the overall efficiency maxed out at 25%. But when you have a phosphorescent or TADF emitter, they can use the singlets and the triplets, so they have a theoretical and in some cases practical value of chi that approaches unity or 100%. And so your efficiency that you can get overall is then going to be much higher. So that's sort of why phosphorescent and TADF emitters are more efficient, as we already talked about a little bit. Phi PL is the photoluminescence quantum yield, so that factors directly into device efficiency. So when you're designing an OLED, your dopant should have as high of a quantum yield as possible. And then finally, eta out is an outcoupling efficiency, which is essentially the ratio of emitted photons that escape the device. So when you generate photons in the emissive layer, the only ones that you're going to see are going to be the ones that come out the top of the device. But the photons in reality can go in all directions. So some of them will go back and be reabsorbed into the device. So you can maximize that. I mean, there's different ways of doing that. I mean, some of it is optics tricks. Some of it is just how the device is made. Actually, one part of it though that's interesting is the way that the molecules align on the surface of the device, because the transition dipole for the luminescence is always going to be oriented in a certain direction depending on the symmetry of the molecule. And so that's going to be the direction that the emitted light propagates from every molecule. So if you can get all the molecules to line up just right on the surface so that there are ways to do it. People have shown that it's possible to at least not necessarily perfectly optimize, but at least improve this situation. So all the molecules are lined up on the surface facing the same direction, and that direction corresponds basically the transition dipole is perpendicular to the surface, all of the emitted light will be emitted perpendicular to the surface, and you'll get a higher outcoupling efficiency. Now, the point of all this, though, from our standpoint, is that the first and the last terms, these two eta terms here, those are both characteristics of the device itself. And using the words of my PhD advisor, that's an engineering problem. It's not really for us to worry about. So if you want to maximize these two terms, that's what the engineers do that work on these. But these two terms here are critically determined by the characteristics of the luminescent molecule that you use. That's again why we evaluate them before we would even test them in a device, and that's why a lot of the concepts that we talked about, fluorescence versus phosphorescence, singlet versus triplet, how to maximize quantity, all that stuff comes into play when you're trying to maximize efficiency of an OLED device. And there are other things beyond here that I haven't mentioned that are still important. So, this is something that we should all be aware of because we motivate a lot of our work in the context of OLED. So all this stuff here is important. And the other thing is that you want, for phosphorescent or TADF compounds, you want the lifetime to be as short as possible. Because if the molecule is sitting in its triplet state too long, you can get triple annihilation, and you can get what's called efficiency roll-off, where you basically populate all the excited states and they're just sort of sitting there parked in that excited state, and when you inject more charges into the device, the ones that are in the excited state haven't relaxed yet, and so you're wasting charges that way. So you'll often see for any OLED device, but especially if they have long photoluminescence lifetimes for the emissive layer, you'll see your efficiency as a function of current or voltage will be kind of flat for a while, and then it'll start to dive off, and it'll dive off because of, again, as you inject more charges in, if the lifetime is too long, those molecules haven't relaxed yet, and those charges can't be used. So and also there's more likelihood of triple annihilation pathways and things when your lifetime is too long. So you want your lifetime to be as short as possible for the emissive dopant as well, in addition to having a high quantum yield. So that doesn't directly factor into the efficiency, I guess, but it'll sort of determine this chi value a little bit, and as well as possibly this eta R term can be determined to some extent by the lifetime. So both quantum yield and lifetime are important, as well as the color profile, all those things that we talk about for OLEDs. All right, I think that's my last slide. It is. So any questions on what we covered today? All right, so I think that's it for the workshop. So let me stop the video.